Nuclear fusion is a process that powers the stars, including our sun, and is the source of energy that fuels the radiant glow we observe from these celestial bodies. To understand this process, one must delve into the forces and reactions that occur at the atomic level. In the cores of stars, where the temperatures soar to millions of degrees and the pressures are immense, nuclear fusion thrives as the dominant reaction. Fusion reactions involve the joining of two light atomic nuclei to form a heavier nucleus, accompanied by the release of energy. The most common form of nuclear fusion in stars is the fusion of hydrogen nuclei, or protons, to form helium. This includes a series of reactions known as the proton-proton chain reaction in stars like our sun. The proton-proton chain reaction process begins with two protons colliding at incredibly high speeds and temperatures, overcoming their natural electrostatic repulsion. When these protons come sufficiently close together, the strong nuclear force takes over. This force binds them together to form a deuterium nucleus, which consists of one proton and one neutron, a positron, and a neutrino. This reaction, by itself, releases a negligible amount of energy. It is part of a chain-producing effect which culminates in the formation of helium-4. After the formation of deuterium, the next reaction in the chain involves another proton colliding with the deuterium nucleus to produce a helium-3 nucleus, a gamma ray, and the release of energy. Then follows one of the notable final steps in the common fusion process in the sun. Two helium-3 nuclei collide, resulting in the creation of one helium-4 nucleus and releasing two protons. The entire sequence liberates a tremendous amount of energy, primarily in the form of kinetic energy of the particles and electromagnetic radiation. This energy eventually radiates outward from the core to the star's surface. It emanates into space as sunlight and other forms of stellar radiation. In more massive stars, fusion processes involve heavier elements and go beyond hydrogen to include elements like carbon, nitrogen, and oxygen in the CNO cycle. These reactions are more complex and efficient in energy production, but also require much hotter temperatures than those found in less massive stars. Not only does nuclear fusion provide the energy necessary for a star to shine, but it also plays a pivotal role in the cosmic evolution of elements. As stars exhaust their hydrogen fuel, they begin to fuse heavier and heavier elements. They continue until they reach iron in their cores. Beyond iron, fusion no longer releases energy, but rather requires it, leading massive stars to begin collapsing and potentially exploding as supernovae. These supernovae disseminate these elements throughout the universe. In summary, nuclear fusion is the engine of a star, converting light elements into heavier ones while releasing energy that supports the star against gravitational collapse. It contributes to the synthesis of elements that form planets and living organisms. Understanding this process helps scientists comprehend not only the life cycle of stars, but the very nature of the universe.